All right, well, it is my great pleasure to introduce Sean Griffin's talk. This is his thesis defense. It's really been wonderful working with him all these years. He's going to be talking about ordered set partitions, Garcia and Procesi modules, and rank varieties. And please feel free to ask questions either in the chat or by interrupting, but maybe preferably by the chat. And Sean, if you don't mind, I will monitor the chat for you so you don't have to keep eyes on it.
Okay. Thank you, Sarah. And yeah, I wanted to first say thank you to Sarah Billy, my advisor, for her excellent mentorship throughout graduate school. I want to thank my parents and my siblings and my partner for their unwavering support. And the committee members. And there's one committee member who couldn't make it here today. That is Steve Mitchell. He passed a few years ago from cancer. So I wanted to thank him as well because, yeah, a lot of his comments stuck with me throughout graduate school and helped me become better as a mathematician. Okay, so today I'll be talking about certain families of rings with connections to multiple areas. So first, combinatorics, we'll see that these rings have nice dimension formulas counted by combinatorial objects. In representation theory, these rings will have symmetric group actions, and I'll identify them as symmetric group modules. And also some geometry, these rings have connections to cohomology and coordinate rings of varieties. And our prototypical example is going to be the coinvariant ring, which I talked about briefly in the pre-seminar. I won't assume that you went to the pre-seminar, but I'll go through the coinvariant ring quickly. So what is the coinvariant ring? So a little bit of notation. X sub n will be a set of commuting variables, x1 through xn. Q bracket xn is the polynomial ring in those variables. And Sn is the symmetric group of permutations of the letters 1 through n. And we'll say that a polynomial is symmetric if it's invariant under that Sn action, permuting the variables. And we'll let the symbol denote the ideal generated by all positive degree homogeneous symmetric polynomials. It's called the ideal of invariance. And the corresponding quotient ring is called the coinvariant ring. And we'll denote that by Rn. So modding out by all of the positive degree homogeneous symmetric polynomials. And Rn, the coinvariant ring, has many nice properties. The first, you can write that ideal in terms of a nice set of generators, E1 through En, where Ed is the elementary symmetric polynomial. It's just the sum over all of the square-free monomials of degree d. So here I give an example of the elementary symmetric polynomial E2 in a set of 3 variables. It's just x1, x2, plus x1, x3, plus x2, x3, which is clearly symmetric in the variables. And it has a nice dimension formula. Its dimension is just n factorial, which is the number of permutations. And Artin found a nice monomial basis. So this is the set of monomials where the degree of the ith variable is at most I minus 1 for each I. So this monomial basis witnesses this fact that the dimension is n factorial. Another way to see this, or another refinement of this dimension formula, is a characterization of Rn as a symmetric group module. Rn is isomorphic to the regular representation. So the free vector space spanned by the permutations Sn. This is called the regular representation. And it also has a nice Hilbert series formula, which we discussed in the pre-seminar. So recall that given a graded vector space V with graded components Vi, its Hilbert series is the Q generating function over the dimensions of those graded pieces. So sum overall I of the dimension of the ith piece times Q to the I. And then in the special case where V is Rn, it's graded by the total degree in those variables, xn. And the Hilbert series has this really nice formula, which you can see from the Artin monomial basis. It's the generating function over the inversion statistic on pi. So here, inv of pi is the number of pairs where pi I is greater than pi j. Or you could write this as a product, which is called the Qified n factorial, which is the product of 1 plus q, 1 plus q squared, and so on. And it also has some nice connections to geometry. And maybe better known is the first way, which is better known, is as the cohomology of the complete flag variety. So we'll say that a complete flag in this vector space C to the n is just an ascending chain of subspaces of that vector space C to the n. So V dot is this sequence of VIs, where VI is a subspace, where the dimension of the ith vector subspace is I. So you could visualize this as, first you start with the origin, so a point, and then you choose a line going through that point, and then you choose a plane passing through that line, and so on until you get up to the whole vector space Cn. And then the complete flag variety, which is, if you've taken the manifolds course at University of Washington, you've probably seen the complete flag variety, at least briefly in Jack's book. It's the set of all complete flags in C to the n. This is one way to define it. It's a homogeneous space. And Borel, in 1953, realized or proved that the cohomology ring is isomorphic to that coinvariant ring, Rn, as graded rings. And the second geometric realization is, which we discussed a little bit in the pre-seminar, is as the coordinate ring of the scheme of nilpotent diagonal matrices, which was proven by Costant. I'll come back to this later in the talk. So here is a bit of an organizational table. We just discussed Rn, the coinvariant ring. We saw that its symmetric group module structure is it's isomorphic to the regular representation, Q span of the Sn. And you can also realize it as this cohomology ring. So I'll introduce two more rings, two other families of rings, which both generalize Rn. So let me discuss R lambda first. Oh, sorry, before that, basically my contribution, I wanted to say my contribution is to introduce a new family of graded rings, R and lambda, which generalizes all three of those families of rings. Sorry, all three families: Rn, R lambda, and Rnk. So let me move on now to R lambda. Oh, sorry, another slide. Okay, and my main results will be formulas for those rings, R and lambda. So formulas for the graded symmetric group modulo structure of that ring, and also some applications to geometry. So applications to the Eisenbud-Saltman rank varieties. Okay, now it's the next slide. So cohomology of a Springer fiber is our next family. So before I define that ring, first let me review some partitions. So an integer partition of n is just a sequence of positive integers, lambda 1 through lambda l, which weakly decrease and sum to n. And you can visualize a partition using its Young diagram. So this is the diagram with rows of boxes where the ith row from the bottom in French notation is given by the ith part of lambda. So we'll draw 4, 3, 1 as this row of boxes with 4 on the bottom, 3 in the second row, and 1 in the third row. In the conjugate partition, which I'll denote by lambda prime, in terms of the Young diagram, you take this Young diagram and you reflect it across the diagonal. Or in terms of, another way to say it is that it's the partition that records the sizes of the columns. So that in this case, the conjugate partition is 3, 2, 2, 1, because the columns are sizes 3, 2, 2, and 1. And we'll visualize this as the Young diagram, 3, 2, 2, and 1. Okay, so on to Springer fibers. So given a partition of n, I'll let X be a nilpotent n by n matrix, such that the Jordan block sizes are recorded by that partition. So as an example, if lambda is 3, 2, then in Jordan canonical form, this matrix would look like a block matrix of size 3 and then a block of size 2, where the first block looks like this, so zeros on the diagonal. Second block looks like this. Notice I need zeros on the diagonal here because it's nilpotent. All of the eigenvalues are 0. And then we'll define B lambda as a subspace of the complete flag variety. It's all of the complete flags that are invariant under acting by that matrix. So all of the V dots such that when you act by X on VI, it's contained in VI. And so as a special case of this, you get the flag variety back. If you take lambda as the partition with all ones, so this is my notation for partition with all ones, then what's a matrix with Jordan type all ones? Well, it has to be the 0 matrix. But if X is 0, this condition is trivial because the 0 subspace is always contained in VI. And so the Springer fiber in that case is all of the complete flag variety. And one fact I really love about Springer fibers is that, so this is a variety, but it has multiple irreducible components. So it breaks up into smaller pieces in a way. And those irreducible components are in bijection with standard Young tableau of that shape lambda. And so Springer was the first one to realize that although the symmetric group doesn't act on the variety itself in a non-trivial way, it does have an action on the cohomology ring. And he defined this symmetric group action. And he also observed that, and these rings, these cohomology rings also have the property that first, the total dimension of this cohomology ring has a combinatorial formula. It's just n multi-choose the parts of lambda. And a refinement of that statement is that the cohomology ring, you could write that down as a symmetric group module where you take Sn and you mod out by a certain subgroup. So this is called a Young subgroup. It's the subgroup where you allow the first lambda 1 elements to be permuted among themselves, and then the next lambda 2 elements to be permuted among themselves, and so on. And you take that quotient, that set of cosets, and you take the formal linear span of those, and you have an isomorphism as Sn modulus. And also the top cohomology is isomorphic to an irreducible symmetric group module. So the irreducibles are indexed by partitions, and this top cohomology ring is isomorphic to the one indexed by lambda. So you could think of this as a geometric way to construct all of the irreducible symmetric group modules. And you might also ask, well, what about the graded symmetric group module? This is a graded ring. This was characterized by Hatta and Springer, and later Garcia and Procesi. We'll get back to this later. But these cohomology rings, you could write down. You could write down this ring as an explicit quotient ring. So take your partition and write down the conjugate partition, but where you pad on enough zeros at the end to make it a length n partition. And then for each index m, we'll write down the statistic p sub m, which is the sum of the last m entries of lambda prime. And you can visualize this by taking your partition lambda and tack on enough empty columns to make it length n, to make it have n columns, and then count m columns from the right and count up the number of boxes in those columns. The number of boxes is this statistic Pm of lambda. And the Tanisaki ideal I lambda is this ideal given by certain elementary symmetric polynomials, except this time we're going to take ones in subsets of the variables. So we'll throw in this ED of S for S a subset of variables if a certain inequality holds. I don't expect you to, absorb this inequality all in one go. We're going to do an example on the next slide. So let R lambda be the corresponding quotient ring, where you mod out by I lambda, and Concini-Procesi and Procesi, and also later Tanisaki proved that R lambda is isomorphic to the cohomology ring. So for example, you could put it into a computer and compute things about it.
Can I repeat the question there? Alex is asking, what do you mean when you say S is a subset of Xn? So maybe he forgot what the Xn notation means.
So when I wrote the bold X, that's like the set of all variables, X1 through Xn. And then S is just a subset of that set. So S could be like X1, X3, X4. And then E2 in that subset would be X1, X3 plus X1, X4 plus X3, X4. So the elementary symmetric polynomial of that degree in those variables. Yes, so the slides are online. You can go to my website. Maybe I should. Can someone find the slides on my website? There's a link under research. Thank you. Okay. Okay. So let's do an example of this ring R lambda and write down all the generators. So here's an example with n equals 3 and lambda is 2, 1. Then we visualize our partition like this. Thank you, Nico. And we're going to tack on an extra column to have 3 columns. And when S is size 3, we're counting 3 columns from the right and counting up the number of boxes. That's 1, 2, 3. So P sub 3 is 3. And our inequality is telling us that we're restricting degrees so that D has to be at less than or equal to 3 and greater than 0. So D can be 1 through 3. So you have all of the elementary symmetric polynomials in the full set of variables. Those are all generators. When the size of the subset is 2, then we're just looking at these 2 columns. There's only 1 box. So P2 is 1. So our inequality here is 2 is that greater than or equal to D, which is greater than 1. So D has to be 2 in this case. So you get E2 of x1, x3, or sorry, x1, x2, E2 of x1, x3, E2 of x2, x3. So this is just x1, x2. This is x1, x3. And this is x2, x3. And if you write down this condition, you'll see that basically it's no condition at all. P1 is 0. And the inequality is telling us that D has to be less than or equal to and greater than 1 at the same time, which is impossible. So there's no generators for that size of the subset. And then observe, well, okay, our ideal is doesn't consist of symmetric polynomials because these 3 aren't symmetric, but they are, like the set of generators is invariant under the SN action. And that kind of comes from the fact that this only depends on the size of the subset, not the subset itself. So when you quotient by this ideal, you get an SN module. And okay, so some more combinatorial properties of this ring. It has a nice Hilbert series. So this is just my notation, SCI sub lambda, be all the labelings of the conjugate partition with 1 through n so that you only use each of those letters exactly once, and such that the labeling increases down each column. So here's an example down here. If n is 7, lambda is 3, 2, 2, then you draw the partition with column sizes 3, 2, 2. And this labeling is valid because it increases as you go down each column, and it's standard. And we'll say that an inversion is just a pair of labels, B greater than A, so that either A is to the right of B in the same row, or A is in the next row, but to the left of B. And we'll let inv of sigma be the number of inversions. See, so if lambda is 1 to the n, then you're filling in a labeling of this single row, and you can identify that with a permutation, and then this inversion statistic specializes to the inversions of permutations. So in this example, 4 is greater than the 2, 5 is greater than the 3. So those are the ones in the same row. But then also the 6 is greater than the 5, and the 6 is greater than the 3. So the inv of this sigma is 4. And this is a very special case of the theorem of Hagelin, Heyman, and Lohr from 2005. They proved something much more general, but it implies that the Hilbert series of R lambda is equal to the generating function over the inversion statistic of these objects, these labeled objects. Okay, so we've seen Rn, we've seen R lambda, and let's move on to Rnk. So the generalized coinvariant rings Rnk. These were defined by Haglund, Rhoades, and Shimozono. So given two integers, k less than or equal to n, we'll define Ink to be, first you include the top k degree elementary symmetric polynomials in your generating set, and then you include the kth variable powers of all the variables in your generating set, and let Rnk be the corresponding quotient ring. So for example, when n equals k, Inn is, okay, En down to E1, and then we're also including the nth variable powers, but then it's not so hard to check that this is the same ideal as the one just generated by the e's. So each of these xi to the n's are already generated by the e's. So Rnn is the coinvariant ring. So that justifies the generalized coinvariant ring name. And Haglund, Rhoades, and Shimozono were motivated originally by the Delta Conjecture from algebraic combinatorics. They showed that this ring gives a representation-theoretic interpretation for the expression in the Delta Conjecture when t equals 0 in that special case. The general case is still open. And it also has a nice SN module structure governed by ordered set partitions. So I'll let OP NK be the ordered set partitions of the integers 1 through n into k non-empty blocks. And Sn acts on this set just by permuting the labels, the numbers. So here's an example with 3 and 2. So for example, if you take tau is the transposition that swaps 2 and 3, if you act on this ordered set partition, it'll swap the 2 and the 3 and it'll go to the same ordered set partition, since permutations within a block don't matter. But if you swap the 2 and the 3 here, you'll get a new ordered set partition, that one. And they proved that Rnk is isomorphic as Sn modules to this Q vector space spanned by this set of combinatorial objects, which generalizes the regular representation statement for the coinvariant ring. And it also has a nice Hilbert series. Maybe I'll briefly just say that the Hilbert series is given in terms of the Q Stirling numbers. And it also has a geometric interpretation given by Pawlowski and Rhoades. So they proved that Rnk is isomorphic to a certain cohomology ring, the cohomology ring of the space of spanning line arrangements. That was in 2019, so as graded rings. And there's also a symmetric group action, basically permuting the lines in the arrangement, and that gives you the symmetric group action on the ring itself. Okay, so we've seen the coinvariant rings in these two families of rings that generalize the coinvariant rings. I'd like to move on to Rn lambda. So my contribution is to introduce this new family of rings, which generalize all the previous cases and has some nice formulas. We'll see that it's governed by a certain set of ordered set partitions. So a new family of rings Rn lambda. This time we're going to take our two integers, k less than or equal to n, and now a partition of the smaller integer k. And even though lambda is a smaller partition, we're going to do the same thing to its conjugate. We're going to pad on enough zeros on the right to make it length n. And then define the same statistic where you sum over the last m entries of that sequence. And we'll define in lambda to be this set of, this ideal generated by the set of elementary symmetric polynomials and subsets of the variables. And you might be thinking, oh, this is the same thing as the Tanisaki ideal, but it changes things that this partition is smaller. Since this partition is smaller, then the statistic will be smaller and it forces the degrees to be higher. So these e's are higher degrees than before. EDs. Then in the Tanisaki case. And in this larger set of variables, n variables this time. And Rn lambda is the corresponding quotient ring. Now, it turns out that this quotient ring is actually an infinite dimensional Q vector space. So in order to make it finite dimensional and to use finite dimensional techniques for finite dimensional rings, we're going to introduce another ring where you take an integer s, at least as large as the length, and you mod out by all of the variables to the s power. So this will force the quotient ring to be a finite dimensional Q vector space, and we can argue about its dimension. Okay, and Rn lambda s is the corresponding quotient ring. And the symmetric group modulo structure of Rn lambda also has a nice interpretation. So I'll let OP n lambda s be a certain set of ordered set partitions. We'll let them be length s, so s many blocks, but such that the size of the ith block is at least lambda I. And so for this case of n equals 4, and lambda is 2, 1, yes, empty blocks are allowed. So bi is allowed to be empty. For I greater than the length of the partition. So that's also a bit different. In this case, so if I changed this to a 3, if I changed S to a 3, then I would start to allow empty blocks. But in this case of S equals 2, I'm just taking the condition where the size of the first block is at least 2, and the size of the second block is at least 1. So here are all of those ordered set partitions. And it turns out that Rn lambda s is isomorphic as an Sn modulo to the free Q vector space on that set of objects. Again, just permuting the numbers 1 through n. And what about Rn lambda without the s? This is sort of like the limit. I won't be precise here, but the limit as the s goes to infinity of the previous, of the one with the s in it, because as you allow your variable powers to get higher and higher, the graded pieces will start to stabilize to the graded pieces of R and lambda. So all you have to do is, to get the formula for this, you take the limit as s goes to infinity. So what does that mean? It means allow infinitely many blocks. It's just that all but a finite number will be empty. So this isn't really saying too much, because a lot of the copies of the irreducibles will appear infinitely many times. I have refinements of the statement which are more meaningful. The Hilbert series of this ring. So given one of these ordered set partitions, we'll turn it into a labeling. So we'll associate to it a standard extended column increasing labeling of the conjugate partition. So in the example that n equals 10 and lambda is 3, 2 with 3 columns, 3 blocks, take the first block and use it to label the first column, but increasing down that column. So I'll take the 1, the 3, and the 5, except I have these two numbers left over. I'll just allow them to spill out underneath. And then the 2, the 9, and the 10, the 10 spills out underneath, and the 4 and the 6 start out beneath. And for all of those that spill out underneath, I'm just going to put them into their own cell. So, and I'll call these the basement cells. Each of them gets their own basement cell. And there is a version of inversion for these combinatorial objects. So an inversion is a pair of labels, B greater than A, where either you have the same condition before. So I'll call this a type 1 inversion. Or you're also allowed to, so if B is on the first row, then B can be an inversion with any of the basement cells to the left of it. So I'll call this type 2. So in our case, in our example here, the 3 is greater than the 2, but that's the only type 1 inversion. So that's 1. And then for the type 2, this 10, oh, sorry, the 9, this is the first row. The 9 is an inversion with the 7 and with the 8. But there are no other inversions of type 2. So that's 2. And then to get the right count, you have to sum over all the columns. So the ith column of I minus 1 times the number of basement cells in that column. So in this case, since the 10 is in the second column, I'll add a +1. And since the 4 and the 6 are in the third column, I'll add a +2 each. So in total, the inversion statistic for this case, for this example, is 5 coming from the labels, and then, 3 coming from the labels, and then 5 coming from this extra. So in total, 8. And this is actually, this is not exactly my definition. This is really just a variation on co-inversion statistic of Rhoades, Yu, and Zhao. During the preparation of my article, they came up with this nice inversion statistic, which they call co-inv. It's just slightly different. And they proved using some of my work that the Hilbert series is just the Q generating function over these labeled diagrams. They draw it a little bit differently. It's kind of flipped in their version. And let me also, and they characterized the space of harmonics for these rings R and lambda S. And let me also say there is another statistic which I call D-inv, or diagonal inversion, which also gives a Hilbert series. So it's just the Hilbert series is alternatively the Q generating function over D-inv. But in this talk, I'd like to focus on this inversion statistic, because this is the one that basically stabilizes as you take this limit to infinity. So how do you get the Hilbert series of R and lambda? So for R and lambda, this is like taking S to infinity, which in terms of these diagrams just means you allow basement cells in any column. There's no restriction on where the basement cell can be, just as long as you put them on at the top of the column when you draw it. So I'll call that set of objects SECI and lambda infinity. So in this example, I put 6 in the 6th column. So that means it will add +5 to the inversion statistic this time. And you can imagine if I move this cell over to the right more and more, it just adds 1 to the inversion statistic each time. And the Hilbert series of R and lambda is just the Q generating function over all of these objects, where the inversion statistic is the same one as before. So now let me talk about some of my main results, the first being a graded symmetric group modular structure of this ring. So I'm just going to recall the graded Frobenius characteristic very quickly. Essentially, it's a map from symmetric group modules to symmetric functions. So a symmetric function is a formal power series in infinitely many variables, which is symmetric. And the Frobenius characteristic, it's related to the character of a representation, but it's not quite the same thing. Instead, you get a symmetric function instead of a character. And the defining property is that the Frobenius characteristic of the irreducible indexed by lambda maps to the symmetric function called the Schur function. And then the Frobenius characteristic of a direct sum of irreducibles just maps to the corresponding sum of Schur functions. And there's also a graded version of this. So if you have a graded symmetric group module, V, which breaks up into graded pieces, Vi, then we'll associate to it the graded Frobenius characteristic. So this is the sum over Qi times the Frobenius characteristic of that piece, the ith piece. So the Q's are keeping track of the degree. And we'll let lambda Q be the algebra of symmetric functions, and this the coefficients with coefficients in the field where you join this parameter Q. And this algebra has a nice basis called the Hall-Littlewood functions. I'll denote these by Q lambda prime. Actually, these are the dual Hall-Littlewood polynomials. I think these are also written as H lambda XQ, if you've seen that notation before. And Hatta and Springer, this is what I mentioned at the beginning, towards the beginning. Hatta and Springer, Garcia and Procesi later, using elementary methods, proved that the graded Frobenius characteristic is you take this basis element and you just Q reverse everything. So this means take this polynomial as a Q series and then reverse the coefficients. as a polynomial in Q. This is often denoted by H lambda tilde. Okay. And Rnk also has a really nice graded Frobenius characteristic formula. So if mu is a partition of n, we'll let mi of mu be just the number of parts of mu of that size. And the Q multinomial coefficient is, you take the formula for the multinomial coefficient and you just Qify everything. And Haglund, Rhoades, and Shimozono proved that the graded Frobenius characteristic has this really nice expression. It might be hard to parse at first, but this is just a Q shift times the Q multinomial coefficient times Q prime. And then you take all of that and you reverse it, Q reverse it. And I have a formula for my rings, which is very similar to the previous two. So recall that the multinomial coefficient breaks up as a product of binomial coefficients. And the Q binomial coefficient is, you take the formula for the binomial coefficient and you Qify everything. And I was able to prove that the graded Frobenius characteristic of my rings is a sum with a Q shift times a product of Q binomial coefficients, where this product of binomial coefficients doesn't necessarily collapse into one multinomial coefficient, and then times a Q prime. You take all of that and you reverse it. Okay, I should have said S here because this is specific to Rn lambda S. So what happens if you take the limit as S goes to infinity? Unfortunately, it doesn't really stabilize. So how could you get a formula for the graded Frobenius characteristic when you get rid of S, when you take the limit as S goes to infinity? And we'll do this in terms of the inversion statistic. Good question. You caught me. So where does S come into the formula? Hidden in this expression is a definition that mu 0 prime is defined to be S. Yeah. So how do you get a formula for Rn lambda? Basically take those labeled diagrams, but now you allow repeated integers. And we'll define the same inversion statistic as before on these non-standard fillings. So here's an example where you have 4 ones, just as long as we just need that the labeling weakly increases as you go down each column. And it's a theorem that the graded Frobenius characteristic of this ring is the sum over all of these labelings, where you keep track of the inversions, but you also keep track of a monomial corresponding to the filling. So as in an example, for this phi, x phi is just the monomial recording how many times each label appears. So we have 4 ones, so it's x1 to the 4. We have a 5, so x5, x6, x7 squared, x8, and x9. Okay, so, okay, how hard is it to show it's symmetric? In this formulation, it was hard, but for this, so the existence of the D-inv statistic was necessary for me because it was hard to prove that this was symmetric, but it's easy to prove that the D-inv formula is symmetric because the D-inv formula gives you an expansion in terms of LLT polynomials, which are known to be symmetric. Just LLT polynomials, which are not Hall-Littlewood polynomials, more general LLT polynomials. And then there's a bijection which moves you back in between these two statistics. Great question. Okay, so so far we've seen these 4 families of rings. I've kind of run out of time, but there's also this other story in terms of a coordinate ring. So I was able to realize this ring Rn lambda as the coordinate ring of a certain scheme-theoretic intersection. So let me just show you the slide. So this is a geometric realization of Rn lambda. This is the previous case for the Springer fibers. It's known that De Concini and Procesi proved that this cohomology ring of a Springer fiber is isomorphic to a certain coordinate ring, where you take some nilpotent orbit closure and you scheme theoretically intersect with the diagonal matrices. In my case, the R lambda rings come from Eisenbud and Saltman rank varieties. So this is the set of n by n matrices such that some rank condition holds, where you allow not just nilpotent matrices, but also matrices with higher rank. And Eisenbud and Saltman conjectured a generating set for the vanishing ideal, which Wayman then proved. And as an easy corollary of that, you get this isomorphism as graded rings and graded SN modules. So Rn lambda is isomorphic to this coordinate ring of a scheme theoretic intersection between the rank variety and with the rank variety with the diagonal matrices. So you can use, my formulas for Rn lambda give you basically the Hilbert series and the graded Frobenius characteristic of these coordinate rings. Okay, and I think I'll end. Oh, and last slide, not ending yet. Further directions. I mentioned earlier that the RNK rings, the motivation behind that was from the Delta Conjecture. The Delta Conjecture is this conjecture about symmetric functions and this McDonald eigenoperator delta prime. So it would be interesting to know if my graded Frobenius characteristics, if that also has a nice expression in terms of these operators. And then a second direction would be, what is a major index statistic for these labelings? I only told you variations on an inversion statistic. So how could you define that? Haglund, Rhoades, and Shimozono have one for their case. So I think I'll end there. Thank you.
If you want to put something in the chat to thank the speaker, or you can use your little reaction button. Now everybody can see. Applause is always a little bit different electronically, but awesome job, Sean. So I want to say that the paper that Sean, that the talk is based on is already on the archive, right, Sean?
Yep.
And he's got an abridged version too that was accepted as a talk at FIPSAC this summer in July, just so you know. All right, so are there questions for Sean? Daria, is that a hand?
Albeit, so you have Hilbert series. Do you have basis for them, or did you prove them somewhere in a different way?
Yes, I have bases for them. It's a variation on the staircase monomials from the RNK paper.
So some mix of powers and keys polynomials?
I haven't found any connections with key polynomials yet. So in particular, I don't know what a Grosvenor basis for these ideals is. I used techniques mostly from the Garsia-Procesi paper, and they get around having they don't need a Grosvenor basis for that.
Oh, so you have a basis for the quotient without a Grosvenor basis.
Yes, yes.
Interesting.
Yes.
It's like one of these, like a kicking basis.
Yes, it's a generalization of the kicking basis.
Brennan?
Yeah, wonderful talk. So I was wondering, do you have anything like an Adin, Brinty, Reuchmann style refinement? So I mean, they have this thing with kind of like set valued statistics, like descent sets rather than just Maj. I mean, I guess this is kind of tied into looking for a major index basis. Like my student Kyle Meyer is something for R and K, but for R and Lambda S, is there anything in that direction?
I don't know yet. Is that known for R Lambda?
It's open for R Lambda, to my knowledge.
Okay. Yeah, I don't know yet.
Okay, cool.
Great question.
All right. Well, if that's the end of the questions, then thanks again, Sean. That's really good.